My name is Sam Becklar, and this is my lab report for Physics 2211, Lab 2, Motion of the Falling Objects. Let's get started with a brief introduction. The purpose of this lab is to observe the motion of an object that is dropped from rest. Key concepts and fundamental physical principles include Newton's second law, terminal velocity, gravitational force, weight drag force, and the motion of a falling object. A preview of our results is that the following object will reach the terminal velocity when the gravitational drag forces cancel out. Here's a deeper look at the explanation and reasoning behind all of our physics concepts and how they apply to this lab. Here are some important equations we'll be utilizing in this lab, including Newton's second law, also known as the momentum principle, the position update formula, velocity update formula, net force formulas, and formulas for both drag and gravitational force. These equations will be implemented in our CloseScript code using Python. Let's take a brief look at some models. Here are three relevant free body diagrams. The one in the top right, without drag, represents our first computational model. The bottom right accounts for drag force, but at a point where it is less than the gravitational force, thus the paper velocity is less than that of the terminal velocity we will experience. This is our predicted model. The diagram on the left is in a state where the gravitational and drag forces are equal and opposite. Thus, the velocity in paper is equal to the terminal velocity. Our second computational model with drag force will reach this balance. Time to dive into our experiment. For our experiment, the system is a piece of paper, and the surroundings are everything else. For the procedure, we dropped a crumbled piece of paper from rest and allowed it to fall from the ground to the ground. We calibrated this with a meter stick and recorded a video of the motion process to import into Tracker to extract the object's observed position versus time. Then we constructed a computational model in CloseScript that includes only the effects of gravity and the paper. We constructed a second computational model that accounts for both the effects of gravity and the effects of drag on the paper. Then we compare it to all three models on the same graph. Finally, we will analyze results and draw conclusions. Key assumptions we must make in this lab are that only the gravitational and drag forces act on our system. These forces do not cancel out until they reach terminal velocity. Until this point, the net force is not equal to zero, which causes acceleration in our piece of paper. Here in Tracker, we gather data points from our video after setting the origin and calibrate which, after plotting the data, yielded the observed position versus time graph we see here. Now, moving on to our computational models and code. Looking at the code for the computational model without drag first, here are the initial conditions. I set t equal to 0 because this is the timestamp the paper starts falling in the video, and the position is 0.2270, while velocity is the 0 vector. At the start, delta t is 0.001 because this is the Tracker time step, and b equals 0 because there is no drag force here. In the calculation loop, that force is just equal to weight, so I added the equations to calculate weight and then updated the net force. Here we have the computational model without drag, including both the position versus time and velocity versus time graphs, as well as the animated visualization. Note that the green arrow off on the object represents gravitational force, the only force acting on the system in this circumstance. The initial conditions for a model with drag are all the same except that b is proportionally constant to the magnitude of the drag force, and the magnitude of the drag force is no longer 0. The calculation loop also differs here. We must add the equation to calculate for drag, and now our net force equals not only weight, but weight plus drag force. We also had to set a new arrow scale. Something that hasn't changed is that both models use the position and velocity update formulas to derive data points for our resulting graphs for each time step. Here we have the finalized computational model with, as you can see, an orange arrow indicating the drag force that was missing in our previous computational model, and of course we still have gravitational force acting on our piece of paper as well. Finally, let's discuss our conclusions for this lab. Here we see our three different graphs presented all together. One difficulty here is that it's hard to see the computational model without drag force because it so closely correlates with the other computational model with drag force. However, it is easy to see that our experiment never met the terminal velocity that we had predicted due to errors we will discuss in the next slide. A possible source for error in my predicted Tracker data is that we were the ones dropping the piece of paper, so there was room for human error that would have altered our initial conditions. Also, if only gravity were acting on the paper, then it would have fallen straight down, but instead it started veering to the side as time progresses. So although we assume air resistance to be 0, this is definitely not the case. Many factors can improve my experimental model, such as equations that accounted for more outlying factors in the situation and better overall understanding of the intended results. Also, my paper was not crumbled symmetrically, which probably led to non-zero air resistance problem we encountered. It was like a poorly constructed paper airplane. Sometimes, something along the line of a ball, as we used in the starter code example, would be more fitting. We mentioned the concept of terminal velocity previously, which means the force of drag pointing up has exactly balanced the force of gravity pointing down. Which of these models, if any, predicts terminal velocity? The only model that predicted the terminal velocity was a computational model with drag force, since the other two models didn't account for drag force, so it is unable to cancel out the gravitational force if the paper was thrown downward instead of dropped at rest. The terminal velocity should be the same as the initial case, since gravitational force, which is a constant, and drag force will still balance out at the same velocity per the definition of terminal velocity. We just discussed these forces must be equal and opposite and dependent on whatever the initial velocity of the system is. Thank you for watching my lab report and have a great day. My name is Sam Becklar, and this is my lab report for Physics 2211, Lab 2, Motion of the Falling Objects. Let's get started with a brief introduction. The purpose of this lab is to observe the motion of an object that is dropped from rest. Key concepts and fundamental physical principles include Newton's second law, terminal velocity, gravitational force, weight drag force, and the motion of a falling object. A preview of our results is that the following object will reach the terminal velocity when the gravitational drag forces cancel out. Here's a deeper look at the explanation and reasoning behind all of our physics concepts and how they apply to this lab. Here are some important equations we'll be utilizing in this lab, including Newton's second law, also known as the momentum principle, the position update formula, velocity update formula, net force formulas, and formulas for both drag and gravitational force. These equations will be implemented in our ClosesScript code using Python.